Good morning and welcome back to Scientific Visualization. I know the Pro is kind of new. It's I had it in the late night coding sessions for a while to distinguish advanced topics from basic topics, and then I recently decided, hey, let's just put it in for master's classes and leave it out for bachelor classes. So it's kind of new. I think I use it for 2 weeks or so for the official lectures. No big deal though. Okay, so where are we? We are doing scientific visualization here, and last time I started with flow. And after showing you a video on flow visualization that was a little bit dated, 1963, I now looked it up. So it's quite an old video. My point was that we're still using, at least to some degree, similar visualization techniques. And as I'm motivated at the very beginning of this lecture, a lot of the things that we do are conceptually 1,000 years old, which is no surprise given that, well, it's still sort of the same humans that look at those images. So while sometimes we develop new techniques, in particular through the use of computer, it's actually pretty often the case that things that used to work a few thousand years ago still do it today, or a few hundred years ago. Okay, now back to flow. So the first thing that I talked about were arrows. So little glyphs. Here's a zoom in into a graph, into a flow field visualization, flow field graphics. And as I'm motivated, these arrows kind of work. Okay, so if you look at this, it's pretty obvious what's going on. It doesn't require a ton of explanation here. Maybe it requires a little bit of explanation where the field is from, or why there's two different types of arrows, magenta ones and yellow ones. But other than that, it's pretty obvious what's going on, right? Apparently flow is kind of going this way here, and there's a vortex, and there's another bunch of vortices there. So the first pro argument for arrows or glyphs in general are, well, they're super intuitive, require no explanation. We can use them to visualize flow to layman people, which is not a thing that is kind of in your DNA. It's literally, it's not a born instinct or whatever, but you are trained. Everyone is trained to use arrows for visualization of vectors. You do this at school very early on, and you do this for years. So it's kind of a thing that we're trained to use. And I've also mentioned that there's a historical reason for that. So the assumption is that this is based on this gatherer hunter, in particular the latter one, hunter culture that, well, our ancestors used to kill prey using arrows, literally, and those have the tendency to fly into a particular direction and, well, effectively kill something. But this idea is that an arrow flies into a direction. So it's something that moves through space. So we're kind of used to it. Our culture is used to interpreting arrows as a direction. And we see them in signs, so they're just all over the place. Which is kind of an interesting argument to make, that if a culture that is not based on this hunter concept might not be able to understand arrows at all. Does something like that exist on Earth? Yes, it's pretty rare. I mean, it's fairly uncommon for any culture not to have a global influence, but there are some cultures, very remote people, that have not had a significant impact from kind of a global community, and some of those are actually not based on, they're just based on gathering, not so much on hunting. So there could be technically issues with arrows, not on Earth, I suppose, but another interesting kind of anecdote here is that when the Voyager probes were sent out into space, they carry this golden record. You can look this up if you're interested. Look for golden record Voyager. Literally a record, Schallplatte in German, right, that contains both audio recordings as well as video recordings. Well, images. So now the trouble is, you can't ship a record player along with a space probe, or you could, but it's really heavy. So the idea was to give some aliens, whatever, that picked this probe up in millions of years, some idea who sent it. And it contains a description how to play this thing. It's kind of a funny thing, so people spend a lot of time how to, like, get some alien culture to understand what our notion of time is, how fast they should play this record, that they should spin this whole thing at all, and that it contains audio and video material, and so on and so forth. So they spend a lot of effort on this golden record. And one interesting fact is that it contains a ton of errors. So the description contains a couple of errors to explain things. And like years later, literally 10 years later, after the probe was released, someone wrote an article saying, okay, well, this might totally not work for an alien culture if they are not based on hunting, if their kind of basic background is not based on hunting. I suppose hunting is probably pretty universally based on something that is get thrown, but if it doesn't, or if that culture never hunted, then they might have no clue whatsoever what errors are. So that's an interesting thing. However, let's literally keep things low profile here, and let's assume that the visualization we design are for Earth-born people. So in that case, we're pretty safe with errors. So, but there are other issues other than alien problems with these errors or glyphs. So here you can already spot that there's situations where those errors might clutter the screen, or there's situations where their appearance might be relatively sparse. So there's potentially a part, here's another part that is completely void of visualization information. Hence, we don't really know what's going on. Here's another example using ellipsoid-shaped glyphs over arrows. That is particularly interesting when you don't really care about the direction so much. Sometimes you just care about the orientation of the field. The direction doesn't matter maybe. But there's other things that you might want to encode. For instance, the isotropy. How much does a field point in one direction, or does it vary? And then you want to scale your glyph into multiple dimensions, and then an ellipsoid is kind of useful. But again, here a similar problem is relatively sparse on the outside, and also when we scale, for instance, magnitude of the field, magnitude of the vector field, we use that to scale the glyphs, which is a pretty common thing. Then, well, here our scale basically makes all those glyphs disappear, and in the center it's all cluttered because apparently a lot of stuff is going on. Another anecdote about vectors. I mentioned this this concept of scaling glyphs in pretty much any Viz lecture. I mean, why shouldn't I? And most people agree that it's a good idea if you have a high magnitude, so things flow fast, to use big errors, big glyphs. And in regions where things go slow, to use small errors, right? So that is also something that is fairly intuitive, I would say. However, it turns out, so when I do this, it's kind of hard to do this here on Twitch, but if I do this in present and do kind of a service like, okay, how would you approach this problem? If you have slow fields, would you use small errors or large errors? Like kind of turn the whole thing upside down, right? Use in regions where the flow is slow, where the gradient is small, use a big error or a big glyph, and vice versa. So while that sounds totally counterintuitive, there are usually, like, I haven't done like an empirical study on this, but I would guess there's like 2 or 3% of the people present that would actually do it kind of the opposite. And when I first saw this decades ago, I was like, okay, well, sure, student didn't pay attention or has weird ideas, which sometimes happens. And then I started to ask, like, why would you possibly do this? I mean, it's a fast flow, it's a high magnitude, so make this thing big. I mean, sounds pretty obvious. And one student gave me this very interesting argument that he said, like, okay, well, that's all fine, but in particular, if you look at an image such as this one here, so what happens? These big glyphs, they cover a ton of space, and the small glyphs don't. Now, if you would actually throw dust or anything at a flow field, what happens? Well, in areas where the magnitude is fairly slow, matter will start to accumulate, right? So you get fast influx, and then things are stuck there, and then they potentially flow out fast again. So if you have like a bottleneck or anything. So if you have this bottleneck situation, what do you see? Well, you see very little matter, let's say dust, very little dust at the fast flowing region, and a lot of dust at the slow flowing regions. And that's what you get here. So to make a long story short, I found that this is, while I still use large arrows for for regions with a large magnitude, I think he had a pretty valid point. So there are also arguments for doing it vice versa. So what that means, in summary, while glyphs are simple and they are intuitive, there's some issues with them. Well, first of all, never mind the alien issue. I guess we can live with that. But there are some issues that you can interpret things differently. Okay. Then there are big issues, occlusion effects, right? If you scale things up, they occlude stuff behind. So issue here. When you have significant changes in magnitude, so you have very fast flow or very I don't want to say large, very well, high magnitude. Let's stick with a mathematical term here. So you have a very high magnitude at some places and a rather low, maybe a millionth of the magnitude in other places. You have issues with scaling. You can't scale one error a million times bigger or smaller because it's certainly going to disappear or cover everything. So you probably have to use a non-linear scale, which is always hard to interpret. You can also use color if you want to. I've used this on the images before, but again, color is kind of hard to interpret. There's a lot of research in visualization on color, on how to choose color maps in particular, and how to not choose them. that's maybe even the larger body of research, how to not choose the color map. And it's kind of a big deal, and it makes things less intuitive. So pros and cons, I would say. Okay, so let's look at other concepts of how to visualize a flow field that might be a little bit more elaborate and maybe get some of those drawbacks out of the way. And what I want to talk about are characteristic curves. The video, the 1963 video, actually spent a lot of time on those characteristic curves. And what you will see now, if you've watched the video in the last stream, if not, I recommend to go back later and watch it. It's really a nice video. And what I want to do now is pretty much repeat a lot of the stuff that the researcher from well, about 8 years ago said, but again, it's still true. So what we want to do is we want to follow particles. We want to follow massless little things through the flow, and we can visualize the particles directly. We can visualize those particles as they flow, or we can compute their trajectories, or we can compute other characteristic lines, which are not necessarily the trajectories, and visualize those. And there's again a ton of different methods. Here are a few combined, so we can visualize the particles as lines. We can visualize them as arrows. So basically take those lines and break them up into arrows, or break them up into balls or bands, or a couple of things more on that in a few minutes. Okay, so before we start, before we start to talk about the visualization, let's talk about how we can compute those lines. What are those lines anyhow? And there's 4 line types. So there are 4 line types that were also discussed in the video. They're called stream, path, streak, and timeline. Okay, let's start with the streamlines. Okay, the streamlines are something that is very natural to compute in a computer system, and it's extremely unnatural to compute in reality. So again, if you remember the video, streamlines were kind of last. Here I start with the streamlines because they're the easiest to compute, which is kind of a funny thing. So what are they? They are trajectory of these massless particles, but in a frozen or steady vector field. So if you have a vector field, most vector fields change over time, right? So excuse me. So if you have wind blowing, right, it doesn't always blow the same way. It changes, it jiggles, whatever. But if we just stop time, which is very hard to do in reality, but very easy in a computer system, if we stop time and insert a particle into that flow field and let it just be carried away by the flow, then the trajectory of this particle, that's what we call a streamline. Okay. So a path line is now the more natural thing. That's what happens if we insert a particle in the flow and follow its trajectory, while the flow changes over time as well. So that's a path line. And then there's the streak line. And that's also something that you saw in the video. That's what you get when you constantly insert dye, like ink or these hydrogen bubbles. When you constantly insert them at one point, and then let all of those constantly inserted particles be advected for a while, and then stop at some point and take a photograph and look at the trail that you get. Okay, so while the first two lines technically involve one particle that we just track over time, streak lines involve, well, a ton of particles, right? And we just look at their image. Okay, so very different. It's a very different concept, even though it looks similar. And as a matter of fact, in steady flows, it's even exactly the same as the previous ones, but the way we reach that state is very different. And then timelines are, in a sense, orthogonal to the first three. For timelines, we also release a bunch of particles. Let me get out of the way. So we release a bunch of particles that are usually line shaped. So you can also have a spherical shaped or shaped as pretty much anything that you want, but they're usually line shaped. So you release a bunch of particles shaped in a line shape, and then you let this line be advect. Okay, and this can be combined with the other techniques, so you can constantly release these lines or at certain time intervals, and then you get also some patterns. So let's look at what this looks in a computer system. So first of all, let me introduce that visualization here itself. I mean, it's a visualization about a visualization, but first let's explain that. So what you see on the left here, okay, so that is a flow field, a two-dimensional flow field. And what you see are particles that I've introduced into that field. Okay, so they sit somewhere, they start, they get pushed around by the flow, and the whole thing repeats. Okay, so they get pushed around by the flow, and then, well, they vanish at some other point. So and those two axes are simply the x and y axis. Okay, so what you see on the right here is kind of the same, but visualized as a time-space continuum. So here I take the two-dimensional flow field and add a third dimension to it, and that's simply time. So in this case, the blue axis is time. So what you see on both images is literally the same. So each and every plane, so what you see here at some point is visualized here, the plane, but you see the plane moves. Why does the plane move? Well, because time passes. So we have a 2D field at 1 second, a 2D field at 2 seconds, a 2D field at 3 seconds, and so on and so forth. So just having this combined time-space diagram here can be kind of useful, in particular to distinguish the different types of lines that involve time and don't involve time, like path lines or streamlines. Okay, so I hope that's clear. I hope the overall visualization is clear. So let's talk about how these lines are computed. And again, let's start with the streamlines. Okay, so and those lines are really just ordinary differential equations. Sounds like a really complicated thing. In particular, differential equation is one of those scary things, but it's actually a dead simple idea. Okay, and the idea is simply, okay, what's such a line supposed to be? Okay, what's a line in a flow field supposed to look like? Well, it's supposed to start somewhere. Okay, I choose the starting point. Okay, let's say I choose the starting point. So my line at its starting point, let's parameterize it. Let's say we start at 0 and then we end at 1. Okay, so that's just the parameter of the line. So at the starting point, I want this to be a specific point. So I just choose this, okay, x0. And x is a vector, right? So it could be a 2D point, 3D point, 1D point, whatever. Okay, so I just say, I want to be in charge of the point where this line starts. Okay, so if I want to be in charge of that, I'll just set it. I say, okay, well, L0 is x0. Okay, done. And I can choose x0. So how should the line now evolve, behave? Well, what do I want? Let's think about this. I want to, for a streamline, I want to trace a massless particle through a field that doesn't change. Okay, so that was the idea, a frozen time field, whatever, right? So that's just a field that doesn't change. Okay, well, what does it mean that I'm looking for the trajectory of a line? I mean, that sounds pretty strange. So let's try to simplify this and find a mathematical formulation. So if you like try to picture this, you have some sort of flow field. Imagine this being a wind field. Okay, so you have wind, and you've got your particle that you introduce at some point. Like, it's a very small thing. It doesn't have weight, and it doesn't have inertia or anything. So it just gets pulled and pushed by the wind. So what like if I place this somewhere and then I do a long exposure, let's say the particle, even though it's massless and everything, it still glows, okay? So now I take a long exposure image and I insert this particle here and then I let it evolve. And then later on I look at this long exposure image, which is literally what the folks in the 9063 video did, okay? So in this long exposure photograph, okay, what do I see? Well, I see this trail that the particle does. I see this trace. Now, what is this trace really? Okay, let's start at the beginning. Here's the particle. It's at x0, and now there's, let's say the wind blows to my right, to your left. Okay, so let's say the wind blows here. So then what happens? Well, the particle moves here. Now at this point, let's say the wind blows up. Okay, so the particle moves this way. Now let's say at this point, it again is left, so it blows this way. So what is this line really? Or in other words, what is the vector field in relation to the line? Now, if you think about this for a little longer, you will probably come up with this idea that the line is that the vector field is the tangent to the line. Okay, the vector field is the derivative of the line. Why is that the case? Well, the field is always the thing that is responsible for the direction. It's responsible for where will the particle go next. Okay, and since the line is the path of the particle, at every point along the line, the vector field will say, where does it go next? Okay, where does it go next mean? That's the derivative. Okay, that is the change, the rate of change. That's the German, not the German, but that's the explanation of what a derivative is. The rate of change is the derivative. So in other words, here's the mathematical formulation to that. We want the path to have the following relatively simple property. Besides starting at x0, we want the derivative. Okay, so this is here just a fancy way of saying, okay, I want the derivative, the change over u, and u is this parameter, right? It starts at 0 and then counts up. The change along the line should be what? It should be the vector field. V is the vector field here at that point. Okay, I mean the vector field has different values at different points. So I say, okay, the derivative at some point is the vector field at that point at a given time step that I fix. Okay, and that's what makes this a differential equation, because it now contains a derivative. Okay, so this is an equation, right? It makes two things equal, so we call this an equation. The curious thing about these equations is that the results are numbers. Okay, so if you have an equation x equals, I don't know, 5 minus 2, the result is x equals 3. Okay, here the result is not a number, the result is a function. So if you solve that equation somehow, you get a function out. Okay, and the function is, well, your path. No surprise here. So it's an ordinary differential equation because we only compute the derivative in one variable. So it's of the more simple kind as opposed to the partial differential equation that we had previously in the simulation part. So, but it's actually not too hard to understand, I suppose. Okay, so we start at some point and we say the line's derivative is always supposed to be the flow field's value at that point in time. Okay, so I mean, it doesn't say how to compute this. This is not a computational description or some numerical recipe how to do it, but that's just what a streamline is supposed to be. And as a matter of fact, it's a definition of a streamline. So that's here is a definition of a streamline. These things are also sometimes called initial value problems. Why? Because we just know the initial value. This one here, we know where to start. Okay, so in case you read initial value problem, that's the same thing. So that's the streamline. Now let's look at the path line. Path line is pretty much the same, except for one tiny difference here. There's a t in here now. Okay, so there's a t in here because time changes. So I say, okay, well, time changes along the line, so I don't parameterize this line over its length, but over time. So I say, well, okay, how does the line behave 5 seconds into this simulation, or 10 seconds, or 20 seconds? Okay, so previously time for a streamline, time didn't make any sense because time didn't pass. We had this frozen in time sort of vector field thing. So here we simply say, okay, well, the line changes over time. So we still have an initial value problem. So at time 0, we still set the original position. But then we say, okay, at any point in time, this line should behave like the vector field, wherever it is, at that time step t. So the big difference is really, instead of having a constant here, t0, this is now a variable t. And we can use the same variable to parameterize the line. Technically, you could also write u here and then have another equation that says u equals t. I mean, it's okay if that scares you too much. There's too many t's in here, but the key point is really that one. Okay, so now let's look at these two lines in our fancy space-time diagram here. So first of all, let's look at the streamlines. Now, streamlines, as I said, they don't change over time. They're frozen in time. So when I have a time space diagram, I can, for every time step, compute a separate set of streamlines. Okay. So this is what this graphic here is supposed to depict. So every time is the blue axis. So whenever I want, I can say, okay, stop, compute a set of streamlines. Let time continue if I want to. Again, stop, freeze it, compute a set of streamlines, let time continue, and so on and so forth. So here I've just picked 3 sort of random time steps and computed those lines. Okay, so and as you can see, I mean, the lines change continuously. I just picked 3, and on the plane you can actually see what the lines look like. Okay, so again, it's a fixed time step. Okay, or from multiple fixed time steps here. So streamlines are something that, unless you have a steady field that doesn't change over time, streamlines are something that you would never see in reality. So despite the fact that they look like particle lines or anything, they are only particle traces in this very sort of, I would say, theoretical case that your field is steady and doesn't change. Other than that, you can't observe them in reality. So they are purely mathematical, scientific concept to imagine what's the field shaped at any point in time. Okay, so there's in an unsteady field, there's really no particle that follows this line. Okay, because the field changes all the time, and that's what makes this so hard to compute in reality. In a simulation, it's pretty easy. We just say, okay, well, time step here, data, go do the computation. Okay. Now, what is more realistic in a sense, but we're not shooting for realism here, but still, what makes more sense in terms of realism are path lines. Here in that case, particles are started. Let me just replay that animation here. Particles are started at some point in time and space, and we trace them. Okay, so and along those lines, where is it here? And those lines now, they have a direction in x, y, but also in the z direction, in the blue direction, in the time direction. Okay, because the particles h on the left, they were all frozen in time. Okay. So what you generally do is, if you look at those path lines, you just look at the projection. So you're not looking at this time-space diagram, but you're just looking at space. You let the particle start over time, and then you look at the trace just in 2D, which is a projection from the top down. So if you would look from the top along the blue axis and just project everything, that's what you would generally see, and that's what you saw in that 1963 video. So when you were taking this long exposure video, you get this projection along the blue axis. Okay, so because you take all the time steps and combine them into one image, and that kind of crunches it down. That's what a long exposure shot does. Okay, so what's still curious is that when you have an unsteady flow field, when you have a steady flow field, those two things will be exactly the same. Okay, so the path lines would still kind of go up in space-time, but if I project them back down, I would see exactly the same as on those fields, and all of those streamlines here over time would also look exactly the same, because if the field doesn't change, if I do the same computation later, I get the same result. Okay, so those are streamlines and path lines. Path lines are really what you see in a long exposure shot. Streamlines are an artificial thing that doesn't exist in reality, at least not for unsteady fields. Still, the computation is very, very similar, as we will see later on when we implement that. Now, what are streak lines? So first of all, the name streak comes from this a rope that is tied to a little piece of wood, a streak, and then we see how this changes. I don't think that the name is very great, but that's what it is. That's where the name comes from. But again, the idea is that to put tracer particles, to put multiple particles into one point at different time steps, and then look at the evolution of those. Okay, and then later on we connect those points. So here's what that means. So I pick one point here on the left, the big red dot, and then I constantly insert particles. Okay, and those particles, they get advected through the flow. And then what I do is I connect those particles with a line. Okay, so in the previous images again, it was one particle drawing a line, and here's now it's a line that is in between particles that are released over time. You can see that they tend to spread, some of those spread significantly. And how did I find the curved path? That's another story. But you see that it can be pretty tricky to connect them because they might be very far apart. Okay? But nonetheless, a streak line is it's really a set of points. Normally, if we do it in a discrete way, also the streamlines and path lines will end up being a set of points, but the streak lines are always a set of points. So there's no real way to do this in a continuous fashion, right? Because you have discrete point that release. You can space them denser and denser, but it'll always be some sort of a discrete idea. So let's also look at this in this diagram here, in this space-time diagram, and that's going to be a pretty fancy thing. So what is the first question that you might ask, like, what's a streamline anyhow? Like, which of these lines is now the streamlines? You see, there's a lot of stuff going on. So I'll replay that in a second. Okay, so let's just replay that. And before I explain it, there's a lot of lines going on, right? So there's this red line going on up. There's a red line within the time step. Now I'll add a bunch of gray lines, and then there's a ton of black lines on top of that. So first of all, like, which of those lines is the streamline, the streak line? Any idea? Now again, think about this. So we release particles, we constantly release particles into the flow, okay, and look at their combined trajectory, right? So connect their position. So what stuff here in this image? Which one's the streak line? Like these black ones, we've got a red one here, we got a gray one here, we got a red one here. Which one is the streak line? Any idea? So it's actually pretty funny these streak lines are kind of the hardest one to explain, even though it sounds easy, right? They're just throw a die. The red one on the XY axis. Okay, so this one here. So we got one answer. Do we have more answers? Like, what's with this gray line here? Is that also a streak line? Turns out that the answer is yes. So first of all, your answer is correct. How could you tell? I mean, what are all the other lines good for? So what are the yeah, it's just another point of time, correct. So what are the black lines? The black lines are the path lines. Okay, I mean, they look pretty similar to these, right? So those are the paths that each particle released over time takes. Okay, so let's start here. So this is our point in question. That's our initial value point. And over time, we release particles. So this is why there's constantly things starting at every time step, because we constantly release particles. So each of those particles over time takes a certain path line. So those black lines here are the paths of all the particles over time. Okay, so there's first just one path, then there's 2, 3, 4, 5, and then after a while, or after this while here, or after this while here, we have a bunch of particles that have been released. And now the gray lines, and in particular the red line, so the answer is perfectly correct. So the red line is the streak line. That's the kind of the final streak line. So the streak line evolves over time. And those are intermediate versions of that streak line. So the streak line is the line that I get when I connect all the particle positions. And what are the particle positions? Well, they're the result of the particle motion. And the particle motions are the black ones here. Okay, so that's the streak line. So while it's a fairly intuitive thing, okay, release dye in the flow. I mean, this is what you do when you have a wind tunnel, right? Remember the images at the very beginning, the wind tunnel where there was this dust glands, where you have like a very small nozzle and you release dust through that nozzle. Okay, so when you have that situation, you introduce particles, constantly introduce particles into the flow, and you look at their behavior. Okay, so, and that's a streak line. So streak lines are a thing that we most often look at. But to explain them is actually, like, to explain their behavior is actually not that easy. Okay, so those are streak lines. Now let's look at the last part. So there's still some void here. Let's fill that void with the fourth concept, the timelines. Okay, and the timelines are this, as I said, literally orthogonal, because they're generally also spaced or placed orthogonal to the flow. They're an idea that is sort of independent of the previous idea. We just place right at the start, we create a line. And again, you can take any shape, but let's just take a line as shape. So you see particles in a line shape, and then you just look at what happens. So here we start at a line shape, and we advect every particle independently, and we look at how this shape evolves. Okay, so it looks pretty similar to the streak lines, but the difference is here all particles start at a certain time step, and on the left they just start at different time steps. Okay, so those are all the different line types. Okay, before I continue, and I see that I have this on a different slide, but before I continue, I will take a short break. I'd like to take a short break here. Let me just figure out my right slide to do the break and give you literally a break, because what I want you to do is I want you now, at least all the students at the University of Essen, to take a 10-minute break and fill out the evaluation feedback. So I want to do this. I want you to do this now, because generally folks push this off and never do this, but I'm really interested in your feedback. So now I give you a 10-minute break, go to the Moodle page of our lecture, and please fill out that evaluation. You don't have to. You can also take a coffee break if you want to, but I'd be really, really happy if you do. Any external viewers, I'll be back in about 10 minutes when the students have filled this out. You can also do this later on, but I suggest you do it now, because then you don't forget it. Okay. In the meantime, I'll give you a little bit of music. So, welcome back. In case you have done it, thank you very much for filling out the evaluation. So now let's continue. Just one slide back. Where was I? Right after right before I stopped for the evaluation intermezzo, so to say. I was done explaining using these graphs, explaining the basic line types again: streak lines, path lines, streamlines, timelines. Okay, streamlines, top left, this mathematical idea that doesn't exist in reality. Path lines, sort of long exposure photograph. Streak lines, dust or ink in the flow. And well, timelines, well, a bunch of nozzles, so to say, that start and give you a bunch of lines here. Also, what you can see is, so this here is the timeline as it evolves, right? But in between, it creates a surface. And that surface here, you can also think about this, like what is the surface made of, right? Those are path lines, so it's kind of a path time surface. And also that's a thing that was mentioned in the 1963 video. It was a time streak surface. Okay, so you can combine these things. That's what I meant with orthogonal. Okay, so you've all filled out the evaluation, and let's talk about the properties. So what's interesting is that no two lines crossed, except for critical points. Okay, what's a critical point? A critical point is like a source or a sink. That's a point where one of the vector field components, at least one of the vector field components, becomes zero. That's what we call a source or sink. So if everything flows into a single point, that point is a singularity, and that behaves different. But ignoring those points, so that's why I say non-critical points, okay? So at every point in space-time, there's only one streak line or path line, a streamline or path line passing through it. That's a very important property. So these things never cross, okay? So they might pass by, but they never cross. Okay? So this is also nice for debugging. If two of your lines cross, something is completely wrong in your code. Okay, so for streak and timeline, that's different. Many of those lines can pass through a point, the trouble with that property is that it prohibits certain interesting mathematical observations to be done, or it makes them immensely complicated. Okay, so this is also why I didn't. I stopped with this initial value thing. Notice that I've defined stream and path lines as this initial value problem. Where I related the tangent of the flow field to the line. You probably haven't noticed, but I have done this for a very specific reason. I haven't shown you how to do this with a streak line, for instance, right? There was no formula here that said streak line has this relation. It's possible to do this, but it's an immensely complicated process because you have to first compute a different field. So you first compute from the original field a derived field. And that derived field then behaves tangent to that line type. So it's very tricky, and I don't want to do this here. So if you're interested in, I'd be happy to point you to publications that describe this process. Okay, but nonetheless, we can still find numerical ways to compute them. But this relation to the tangent isn't that easy. Okay, so mathematically speaking, they are harder to analyze. So what's also important is, I've mentioned this a couple of times, that the three things, streak lines, streamlines, and path lines, those three things are exactly the same, or in other words, they coincide in a steady field. Even though they are described different, they are computed differently, still, if the flow is steady, you get the exact same result, okay? Or the same line, they coincide, they sit on top of each other. Okay, so those are the mathematical properties. Now let's look at a few visualizations. So here's one that I presented before already. So those are lines, those are streamlines, and in that case, those streamlines are colored with an external property, such as temperature or magnitude or whatever. So you can use different quantities that you can map to scalars to, then map them to vectors, really. I mean, the color is usually a three-component vector, to color these lines to get additional properties visualized. Okay, so you can see, I mean, that's, I guess, a Heria, C Heria, and you can see the exhaust coming out of the nozzles, and then what vortices are created from that exhaust. And as you can see here, we run into similar problems, right? So similar problems to the glyph. So we also create cluttered visualizations potentially. So we also have occlusion, but we can work these things out or mitigate those occlusion problems in various ways. More on that in a second. So what else can we do? Notice that we started with the lines, and then I used color on top of those lines, or I used color to color those lines to get additional properties across. Okay. We can also use other things. We can use, instead of drawing the lines as little lines, we can draw them as little points. Okay. And not just as points, I can draw them as spheres. And what you get then are so-called stream balls. Why would you do that? What's the advantage of a sphere over a over just a line, or set of spheres over a line? Well, the advantage is that I have another I have another parameter to tweak, and that's, for instance, the radius of the sphere. Okay. A line doesn't have a radius, right? I mean, in particular, if I draw it as 1 pixel line, it doesn't have a radius. I could draw it with a certain width. Yes, that I could do. Would result in a similar visualization. One other interesting thing about spheres is that I have this concept of a normal. So they have a surface, they have a normal, and I can compute lighting on top of that. What I can also do is render those lines as tubes, like as cylinders, as curved cylinders. That again gives me opportunity to use radius to make the line bigger or smaller, to make the diameter bigger or smaller, to encode quantities on top of color. It also allows me to, well, use lighting, right? I mean, again, a cylinder is an actual three-dimensional object, so it does have normal, so I can compute lighting on top of that. Why do I always want to use lighting? I mean, what's so cool about lighting? I mean, except that it, well, I don't know, maybe it looks cool or whatever. What's the nice thing about lighting? Well, it's not just that it looks beautiful or whatever, but it gives me better spatial perception. It gives me an idea of how things are oriented. That's what lighting is good for in visualization. Another thing that I can do is I can draw so-called stream ribbons. That is, draw the streamline, streak line, or path line, right? And I can apply this to all line types. Draw it as a ribbon. Draw it as kind of, technically speaking, two lines that are connected. So what's the advantage of that one? Well, the advantage is that I can visualize yet another quantity. I can integrate this, and that's the so-called curl. Okay, because what happens in a flow field is that even though a particle trajectory is pretty straight, if you look at it more precisely, you would see that the particle spins along the way. Okay, and the spin is called curl, and that's an interesting property for some applications. And this you can visualize with stream bends. How does the flow curl? There's different ways how to compute these lines. So one is to literally trace two particles and then connect them. You have to take care that those particles don't deviate from each other. So generally you trace two particles, and then at every step you force them around a common center to keep the radius. So that's one way of doing it. Another one is to compute the curl directly. It's a mathematical property that you can also compute directly. I mentioned that very early on in the lecture, so you might want to go back to the beginning where I explained how to compute curl. So you can also just compute it as a infinitesimal quantity at every point. So that might be an interesting additional property to watch. As a final remark here on just lines, you can also compute what's called shaded lines. So that's lighting computed on top of a line. Okay, so here are two examples. Again, they look pretty nice, but besides looking nice, they also give you great spatial perception. Now the trouble is, first of all, the term shaded lines is awful. The reason it should be called lighted or lit lines, so that would be a proper term, but it probably sounds awkward. And it seems like, in particular, Native American speakers don't really distinguish shading and lighting. So these two terms seem to have a similar meaning in American English, even though they're two different things. But anyways, so it should be lit lines. What do I mean? Well, we compute lighting on top of lines. Now there's an issue that I mentioned a few minutes ago, and that is a line doesn't have a normal. Okay, so a line is nothing that has a three-dimensional representation, really. It's just a concept, right? I mean, a line, just like a point, it doesn't even have an area or anything. Okay, so how should we compute a normal of a line, which is the thing that we need for lighting? So if you're surprised, if you're wondering why is he talking about this normal thing all the time, again, you should probably go a few slides back, a few of my streams back, where I explain how to compute lighting. I do this in advanced image synthesis, I do this in computer graphics, I do this here, or I did this here. But bottom line is you need an orientation. You need a surface orientation to compute the lighting, right? Depending on how a surface is oriented, it changes the color, right? I look at my hand, it's pretty white now, and now it's pretty dark, right? So, and the only thing that changed is orientation with respect to the light source. So the orientation is important, and the orientation is described or quantified by, well, a vector sticking out of the surface, and that's called the normal. So that's why we need that normal. Now, a line doesn't have a normal, so we can't compute lighting. As simple as that. Now, next question, why does it not have a normal? Because it doesn't have a surface. So how do we compute these shaded lit lines? And the idea is as follows. Well, a line doesn't have a normal, but we could say it itself is a vector. It is a normal to another plane, right? I mean, I could say, okay, well, this is the line, and I could say, well, the line doesn't have a normal. I can't say that's it, or that's it, or that it. I could do the opposite. I could say, well, but the line itself is normal to a surface. I mean, if the line goes this way, I could say, okay, well, this is a surface here. So you kind of turn the whole thing upside down and say, well, okay, instead of having a normal to compute the lighting, we'll use the surface where the line is normal to compute the lighting. How is that carried out? Well, you compute this surface that is perpendicular to the line, and out of that surface, you pick the normal that's pointing towards the light source. Okay, so I mean, the surface is made up of a ton of vectors, and you just pick that vector that is closest to the light source, and you pick that as normal, and you compute the lighting. And with that, you get these images here that give you a very nice perception of the shape of the lines. Okay, so it's not about, again, it's not about realism, it's not about nice images. I mean, sometimes it is, admittedly. I mean, visualization folks also like to create cool-looking images, admittedly, but technically, visualization should not be about cool or real. It should be about understanding things. And adding lighting here improves the understanding because we can better perceive the shape. What we're effectively doing with these shaded lines is we're kind of mimicking that those lines form a surface. And you can take this like one step further and say, okay, well, why don't we just compute surfaces right away? Okay, and what you see here are so-called smoke surfaces. And another interesting property about this image here, it's a photograph, or more precisely, two photographs. So those are not computer generated. So those are actual photographs of smoke. I mean, they look very artificial, but nonetheless, those are things that you actually get. If you take a small flame, just like a cigarette smoke or something, you place it in a dark room and you let it evolve with very, very little wind. So otherwise these surfaces, they kind of fall apart. But with very little wind, and then take a flash photograph, you can create these images here, which look really cool. I wouldn't endorse smoking, certainly not. It's a really, really bad idea, but you can make nice photographs with cigarettes at least. So, and what are those surfaces? Well, they are, at the microscopic level, they are made up of a ton of particles, right? Smoke particles, which reflect the flashlight of the camera. So in a sense, those are all a bunch of streak lines. Okay, so that's a combination of a timeline with a streak concept. Okay, so we have this part here where the flame is burning, and it constantly emits toxic smoke, by the way. It constantly emits toxic smoke, and that smoke is made up of little particles, and those particles rise. Okay, so, and when we take a flash photograph, we kind of capture a point in time where a ton of those timelines have evolved along the flow. And we can do the exact same. So while those are photographs here, we can do the exact same in a computer system. So this is a visualization here demonstrating such a streak surface or smoke surface, it's really the same thing, being computed in like computed, run in a computer. So we have a flow field around a cylinder, and we have a timeline. Notice that at the back, so there's a line when it started. You could actually see this line. It'll get turned in a second. Then you can again see the line. I mean, it just looks kind of cool to look at those lines from the other side. And then at some point, we just terminate the computation. So this is why they kind of vanish into void. But it's effectively just a set of streak lines. You can see the line on the left. A set of streak lines that are just connected to form a surface. Okay, and here we've added texture to the surface so that you can actually see the parameterization of the surface a little bit better. And since it's done in a computer system, you can stop it at any time, right? You can stop it at any time. You can stop time literally at any time, and then look at the surface from various directions. So since in a computer system we discretize this, we have the problem that since we have discrete particles that we start, and yes, we can add other fancy effects such as transparency and edge enhancement to it. Since we discretize this, when we look at the underlying data structure, it's made up of little cells, okay? But the surface is excluding parts of itself when it's rendered. So yeah, sure, it's occluding parts when it's yeah. So you need to interact with it. So here's the point I'm trying to get at. So that's the underlying triangulation. Now the trouble is that particles may spread, and we still want a smooth surface. And you can see this here. So as soon as particles spread, you need to introduce new particles to recover the smooth surface. And at some point, you can actually get rid of those particles again if they happen to rejoin, which sometimes happens, and that's just to save computational resources. So the actual computation of that one can be a little bit tricky, because to get those bulbs, you need to introduce new particles. And remember my streak surface at the beginning where I had this white line that was curved, that was based on a similar idea. So as soon as you see, okay, things spread, you need to introduce particles in between, new tracer particles, to get a better idea of what's going on. Okay, so that's a streak surface, but that's basically just combining streak lines with timelines. Okay, again, the black thing here you see on the left, that's the timeline. And as I said, it doesn't have to be a line. I mean, I could do a time loop, right? I mean, I could just start at a loop, or I could start at a rectangle or whatever. And all those things are actually used. They are still referred to as timelines because, like, usually people use lines, but it's you can use whatever you want. Okay, so that's just for the visualization. Now let's before we can visualize these things, we need to solve that equation here. We need to find those positions, and then we can turn them into lines and light them, or into balls, into ribbons, or whatever I just explained. But one thing that I kind of skipped or dodged so far is, like, how do we get that set of positions? Okay, I mean, it's nice that we have this this ordinary differential equation here. Here in that case, you see t, so that's apparently for the path lines. But how do we solve that? I mean, it's not like that this generates a list of points right away. So, and since our data, our vector field, is usually given in some sort of a discrete form, it's usually some sort of grid where we have either simulation or measured, simulated or measured points, we generally employ some sort of a numerical method to solve that. Okay, so numerical solutions are usually the way to go in visualization, because the data we start with is numerical in nature, right? It's already given on a certain grid. We're not given a closed form solution of the vector field in general. Technically you can, but it's a very unusual situation. So now how would you do that? how would you solve this numerically? And let's just go back to what I said at the very beginning, when I said, okay, what's such a line anyhow? And I started with, like, okay, saying this is massless particles without inertia or anything, and I just blow it. I blow it to to a certain point, and then I stop, check the flow, blow it again. So I've already kind of introduced this basic idea of this kind of, you could say, stop motion approach here, right? So we start a point, we move the particle a little bit, we stop, get a new position, store that, move the particle a little bit, stop, get a new position, store that. And this way we get a set of positions. Okay, and I would say that's pretty intuitive as an implementation, as an approach, as an algorithm, as a numerical method to solve this problem. And as a matter of fact, it is a numerical method. It's called the Euler method. Okay, so it's one method to solve such an ordinary differential equation. And it's a very general thing. It's way more general than just this idea of fluid flow. That this Euler method of starting at a point, just adding the current vector to that point, getting a new point, adding the vector to that point, getting a new point. This idea is called the Euler method to solve ordinary differential equations. Okay, so and here it is in mathematical notation. That's the position at a time step t plus delta t. So in other words, the next point. Right? T plus delta t is just a fancy way of saying, okay, well, the next point is, well, the previous point or the current point. Let's say if there's the next, it's probably the current point plus the flow field at that point times delta t. I mean, how long do I travel in that direction? Well, as long as time passes. Okay. So, and we're making some sort of error here, and that I put here as an O term. So that is not perfect. Why is that not perfect? Well, because we assume that the vector field, when I blow, doesn't change, right? I've got this point, and then I make a short burst of vector, make a short burst of, I don't know, air, and then the particle moves, and then I stop, okay? But since the vector field changes over space, in that short period of time, the vector field might already have changed, okay? So I'm making an assumption that it's locally constant. Okay, and that assumption might be wrong. In particular, if delta t is big, right? I've got this particle in a block of, I don't know, 5 minutes, then the particle takes a long path, but it might be influenced by other vectors along the way. So you could imagine that if delta t has an impact, the smaller it is, the better. And through basically the same Taylor series expansion, as I did very early in the lecture, we can figure out that the error here is quadratic. Okay, so again, it's literally the same thing as for the central differences. So you take the Taylor expansion, you check what parts do we ignore, and you realize it's squared. Again, if you have any question on that one, either ask or just go back a couple of slides when I talked about simulation. There I talked about the Taylor series expansion. So, but to make a long story short, what we can do is at a certain point, we can just blow it into one direction and then check. And here you see a situation. So the white curve is the actual path that the particle should take. Now, depending on my delta t, I can either be the big delta t, get this here as a result, and a smaller delta t is this one, and an even smaller delta t gives me that one, so which is better. So the smaller my delta t is, the smaller my error will generally be. But it's a very simple method. I would say it's pretty intuitive, and it's easy to implement. Okay, so you can literally code this up. You can say, well, what's in a loop? So you start with an initial position plus some, I don't know, some time step. Let's say that's 0.1. So it's position plus 0.1 times vector at that point. Okay, you repeat the loop and you get a bunch of points. So it's pretty easy to implement. Okay, again, it gets better with smaller delta t, but there are some issues with this method. And one is that there are situations where regardless of your delta t, you'll never get the right result. A simple situation is if you have concentric circles. So not a spiral, but you have concentric circles. Then your Euler method will always create a spiral. Okay, regardless of how small you choose delta t. Okay, it will always generate a spiral field. Why? Because every vector points outward. And it doesn't matter how small I scale this vector, it'll always point outward. Okay, so a circular field will always create a spiral if you run this through. Euler. And there are other more or harder to see examples. So if you take that field here, for instance, which is an exponential function, and you choose certain delta t's, then you get crazy behavior. So of course, the flow should converge to that point, but depending on how you choose your delta t, it'll actually diverge. So it'll actually get bigger and bigger oscillations. And that depends on a relation between delta t and the function itself. I don't want to go into too much detail here. I mean, you can see this from the yellow lines and just look at the tangents, and you will see that it kind of makes a lot of sense. But the bottom line is it's inaccurate, and in some situations, changing the delta t, or reducing the delta t, will never give you the correct result. Okay, so you will always have something that is inherently wrong. Admittedly, if I decrease delta t here, it'll look more and more like a circle, but it'll always be a spiral. Okay, so it might take more evolutions to for the particle to kind of blow away, but they will always diverge, just like they will do this here with certain delta t's. Okay, so the question is, can we improve that? Can we somehow mitigate those inaccuracies? And there's another issue that comes with this method. That is, if a smaller delta t gives me better results, I have to say, well, I'll just pick a ridiculously small delta t. Well, the trouble is that means the points are spaced pretty close together, which in turn means if I want to see a long line, I need to compute a ton of points. So this method might also be very inefficient. It's easy to compute, but when I have to choose an immensely small delta t, I accumulate a ton of data, so I need a lot of points, and it'll take forever because the computation is serial, right? I take 1 point, compute the next one, compute the next one. So I can't just jump 10 points ahead. So I have to do this one after the other. So that might make this method very slow. So maybe we can take a somewhat more elaborate method and take bigger time steps and get a similar or better result. Okay, so what could we do? Let's look at a simple extension to the simple Euler method, and that's the so-called midpoint method. And the idea here, let's first start with this image here. The idea is as follows. So we start here, okay, and we do one Euler step. So we do one step in the direction of the flow, which would be this way. So we end up at point A. And as you can see, point A, I mean, I've chosen a big delta t, but point A isn't really great. I mean, it's completely off. I would expect this flow to kind of take that part here, and it shoots off that way. But what I can do is I can take, and that's why it's called midpoint, I can take the middle point between that original starting point, which let's say was accurate. I mean, I picked that. And the somewhat inaccurate target point. And then I pick the point in the middle, which is just the average of the two. And I look at the vector there. And the idea is the following. The idea is, well, along that path, the vector field apparently, if it's constant along that path, my point is actually correct. But if the vector field changes along that imaginary direction in which I shoot the particles, then that change would have influenced the particle. And now I can make this assumption and say, well, okay, well, this is one vector here, that's another vector, and the one at the middle is probably sort of the average. It doesn't have to be, right? But I could argue to say, well, I mean, it's probably a good representation of the average of the end and starting point. Okay, so what I do is then I take that vector, I return to my initial position. So I never use point A really, except to compute this point here. I take that vector here and I use that vector at the starting point and say, well, let's go into that direction that I found at the center of the first step, and let's take that vector at the starting point and then end up here. And as you can see, I mean, here it works out pretty well. You can see that the correct path would be this arc here, but we find kind of the same point by just adding C. That doesn't always happen. Okay, admittedly, that's kind of a very nicely shaped example, but certainly this vector here is a better approximation of the real direction than that one. Okay, you can actually prove that it's a better approximation, right? It has a lower residual error. So what do we do now? A little bit more mathematically speaking, Euler step is simply delta x is so the step is delta t times the flow field. Okay. So the midpoint is, well, the middle point between the starting point and the end point. Okay, so we take the midpoint, that is the starting point, plus 1/2 of that step that I do. Okay, so that's my midpoint. And what's the time at that midpoint? To do it properly, we also need to know what the time there is. That's t at delta t divided by 2. Okay, so that's half of the time it would have taken me to reach point A. Okay, at that point in space, I look at the function value. I look at the flow fields value, and that's then what I use to this f mid, that's now this vector here, and that's what I use to modify the original starting point. Okay, so that's the midpoint method. Okay, it takes more computation. I mean, bottom line, it takes 2 Euler steps, right, plus some additional computation. Okay, but it gives you a significantly lower error. So in case you've never heard about midpoint method, and in case you've had a mathematics and numerics lecture before, which you should have had if you attend a master class, so you've probably heard about methods called the Runge-Kutta method, okay, named after 2 mathematicians, Runge and Kutta. And midpoint method is just another name for what's called Runge-Kutta second order. Okay, so there's also a third order, fourth order, there's actually nth order. It's a very general concept, and the Euler method, as a matter of fact, is a first order Runge-Kutta method. So you can increase that concept of taking the center point, take successive version of the center point, and you get better and better. You get more and more complicated methods that take complicated in the sense that they take more computational resources, but that have better convergence properties, and then in the end may well be faster because you can choose bigger delta t's. Okay, so let's just relate this to something that you've potentially heard before in your numerics class, the so-called Butcher tableaus. Okay, so Butcher tableaus are named after John Butcher, and he created a way to graphically visualize or describe these Runge-Kutta methods. Okay, so and that's what you see here, or what you will see in a second, is the Butcher tableau for Runge-Kutta second order, or for the midpoint method. So what you do for this tableau is you take this factor here, so 0.5, that's my weighting factor for the first step. You plug that into the tableau at the center, and here at the left you plug in the time step that you use. So at 1/2 delta t, I use 1/2 of f1 of the first computed method. So this here, oops, where am I? So this here is the row for f1. And how do I combine that? I'll weight that in the end with a factor of 1. Okay, so I'll just take the result and weight it with a factor of 1. So while this sounds awkward, like why would you possibly put this in there if that's here as the function? Well, as soon as those Runge-Kutta methods get higher order, so here's the Butcher tableau for Runge-Kutta fourth order, using that tableau here is a very compressed format of those actual functions here. Okay, so this is f1, f2, f3, f4. So you first compute f1, which is the same as before. It's just basically the flow field itself. Then from that you compute f2, you compute f3, f4, and then you combine all of those into the final result. And you can actually see, okay, well, that thing is shorter than these functions here, but it's a one-to-one representation. I don't want to go into too much of the details. Also, how did I even come up with the Runge-Kutta fourth method? So this is just taking the Taylor series and considering more of the components of the Taylor series. I'm taking more, not truncating that early. If you want to know more of the details, it's in your numerics lecture. It's literally in there, so you probably missed it or forgotten it by now. But this is a very basic stuff to solve ordinary differential equation. I mean, this is in any numerics lecture that I'm aware of when the colleagues talk about ordinary differential equations. Okay, so it's just really a repetition. Bottom line here for us is just we can either kind of go the intuitive route and say look at next point and call this advection, or we can take the mathematical approach, which is really the same, and say, okay, well, use Euler method. It's an ordinary differential equation. What have mathematicians in the last, well, it's calculus, not so many, in the last 150 years, what method have mathematicians developed to solve calculus? And I can tell you that the latter approach is not as intuitive as the former, but it's way better. So just realizing that the things we do are based on mathematical concept, that people have spent an enormous time and brains into solving we can just borrow, steal, whatever you want to call it, ideas from mathematics. Okay, so and that's it. Runge-Kutta fourth order is sort of the standard for high quality flow field visualization. There's an interesting thing that goes on top of that. That is that all of these methods require interpolation of the field, as usual, right? I mean, we need to know values at some point. And there's an interesting relation between using higher order integration schemes and using higher order interpolation schemes. So you can show that higher order integration schemes in combination with low order, like linear, bilinear, trilinear interpolation schemes mess up the quality overall. So you also need to use higher order interpolation. But again, that's a very advanced topic that we can probably discuss in a late night coding session or anything. But just to let you know that if you increase the order of the integration, you also want to increase the order of the interpolation to get a consistent result. Okay. Oh, we got what a good remark here that I apparently overlooked. Maybe I should repeat my math lectures. Yeah, yeah, it probably helps. In particular, knowing that the stuff that you've seen before actually has applications. So I had when I was in my math class decades ago, there were a lot of those situations where it was kind of hard to pay attention because it's like, oh well, it's sure a bunch of numbers and then you get a proof for this, why this works, and but often mathematicians tend to be so happy with their derivatives, lemmas, and proofs that they kind of forget or they deliberately ignore that there are applications for that. So some mathematicians are actually, theoretical mathematicians kind of hate this idea that you can even use the stuff, right? I mean, it's valuable by itself, but I'm kind of more in the practical realms that I say, well, if there's an actual use for something, it's probably easier to remember this or see a sense. But then again, I'm not a theoretical mathematician. So anyways, now that we've got that part solved, okay, somehow we can interpolate, somehow we can integrate interpolation. We'll use linear interpolation here for the most part. And we can advect things, and in the exercise we'll actually ask you to implement just the Euler method. If you want to, you can go ahead and implement a higher order Runge-Kutta method into that framework that we give you in the exercise as well. It's actually pretty straightforward, but the thing that we want you to first start with is the Euler method. Linear multi-step method. So that term doesn't ring a bell. So it sounds like you're talking about something that I would generally call embedded scheme, which means you combine multiple of these orders together to, in particular, use one of the methods to tune the tune the delta t. I would refer to that as an embedded scheme. So I'm not sure if I know exactly what the linear multi-step method is. So long story short, I can't answer your question. So I should probably look that up and check what the German term is for that. But there's one thing maybe as the last note that is sometimes done, which is an embedded method. It remembers always to compute the new one also where you convert. I think I can imagine what is trying to get at, to use the path to increase the order of computation. It's certainly doable. But one thing that is interesting that I've skipped, but since you asked a question here, I might as well mention it here. And that's what's called an embedded scheme. So sometimes you do say a Runge-Kutta fourth order and a Runge-Kutta third order, both together, and then you check what's the difference. If the difference is very low or they're the same, you can assume that your RK3, the third order, was actually pretty good. It was actually accurate already. So maybe the field just didn't change along the path, and then it was accurate. So if they differ significantly, you say, oh, the field seems to be seems to have a lot of changes. So higher order derivatives actually exist or are non-zero. And then what you do is you decrease your delta. So you use the Runge-Kutta fourth order just for one purpose. You don't advect the flow. You don't advect your line with the Runge-Kutta fourth order. You just use it to check how good your third order was. So if you realize there's a big difference, you would then decrease delta t and repeat the process, and then potentially decrease delta t again until they both agree. or agree to a certain epsilon, and then you would continue. So this allows you to do what's called adaptive step size. So that's what's called an embedded scheme, because it embeds one scheme into the other. Okay, so that's one other idea that is very popular, and it's mainly used to speed things up, so to get bigger delta t's while still maintaining a certain quality level. So let's just sum things up at this point. What do we need to do? Well, if we want to do particle tracing on grids, we are given a vector field on a grid. That's kind of the usual thing. That's not really a big restriction. We're generally dealing with grids. So those are outputs of simulation and measurements. We're supposed to solve that thing, to solve that ordinary differential equation. So what we do is we start at a certain point. That's a user-defined thing. So user says, okay, I want the line to start here. So that's our initial value. And we need that. Without that, we can't compute anything. Okay, so we're given this position here, and then we start to do our advection, our solution to that, our numeric solution, Euler, Runge-Kutta, whatever order, and we get a new point. And if we do use Runge-Kutta, we potentially get a bunch of points in between for the computation, but at the end, we get a new point. So what do we do with this new point? We, again, need to interpolate the value, the vector field value, and then we do another integration step. We interpolate the value, do another integration step, and so on and so forth. So we get a bunch of points. How do we get the line? Well, first thing is we could just connect the points with straight lines. So that would give us a line. Another solution would be to, again, fit a line through this. If you want to know what a line is, go back to my older streams in computer graphics where I explained what splines are. So this gives us curved curves, I suppose, curved lines. So which might approximate the original continuous line a little bit better, but in most cases, actually, since those points are usually pretty close together, we just draw them as lines. And as a pseudocode, this thing would look like something like that. We start with a seed point, find the cell in which the seed point is located, find the value within that cell, and interpolate that value, integrate to the next point, get a new point, draw a line to that point, and ultimately repeat the process until we're happy. Happy means either the point left the domain and, well, whatever, it's gone, or we're running out of time. So in essence, you give the accuracy epsilon. Okay, yeah, yeah. So okay, that's for the embed. Yeah, that's an accurate description of the embedded method. And there's more elaborate method that allows you to compute the delta the delta to the delta from the difference between the Runge-Kutta methods. So if you're interested in more details on that, just look for embedded schemes. Okay. So bottom line is we need point location. We need to figure out in which cell the point is. We need to do interpolation, and we need to do integration. Okay, just a very quick note on those three things, and then we're done for today. Point location for a Cartesian grid, trivial. Okay, so if you're in a Cartesian equidistant space grid, in which cell I am, well, trivial. Okay, like if it's 10 cells and they're from 0 to 1 and I'm at 0.5, I'm in the 5th cell. That easy. So mathematically speaking, or algorithmically speaking, it's your position minus the starting position divided by the cell spacing, and then you take the floor of that, and that gives you the cell. So that's easy. Once you know where you are in the cell, you use your favorite interpolation inside that cell. For a quadrilateral cell, we've used bilinear interpolation. And for a cubic cell, if you do this in 3D, and then those are all basically just vectors, three-dimensional vectors, same thing. You get 3D coordinates, you use trilinear interpolation. If you have non-Cartesian grids, that's not here, that's the interpolation. If you have non-Cartesian grid, that might actually be a pain, right? If you have a triangular grid, you might have to go through all triangles to figure out in which one am I. So this point location, while it's super trivial in Cartesian grid, and that's why we love them so much, it might actually be a big deal in irregular grids. And nonetheless, once you've found the cell, you can use your favorite interpolation function, bilinear, trilinear, or just linear in a triangle, for instance. Or you use a higher order interpolation scheme that takes adjacent cells into account. And then you end up with quadratic or cubic interpolations. Okay, so, and then you're done. You know how to interpolate, you know how to do the point location and the integration I explained before, Euler, Runge-Kutta. And you can trace your particles, you can combine them into tubes, into ribbons, into whatever you want, and you get a visualization. You still have this issue with occlusion though. It might be the case that at some points the lines, they never cross, right? But they get pretty close together and occlude everything. And you have some empty spaces where you just haven't started a line, or where no line went into it. Like if I start a bunch of lines here, and the vector field might well be structured in a way that everything gets blown to your left, and nothing is right. So I don't know what's going on here. Okay? A solution to that sort of varying density problem is dense flow visualization. Okay, so what you see here, and that will be the next topic next week, will be how can we generate an image that is inherently dense, that doesn't require me to set a starting point, right? I mean, if I can set something, I can mess it up, right? Any parameter that I give to a potential user might be a parameter that might be chosen in some wrong fashion. So what I want here in dense flow visualization is, I want, in this case, in this example, a 2D flow field, I want an image that covers the entire domain without leaving things out, and in this case gives me such a visualization here. And then I might dig into certain areas in more detail and say, okay, well, okay, so this here is the vortex, what's going on here? And then I zoom in or whatever, and then I place maybe a particle there. But first of all, I want to get this overview and not miss anything. And that's what dense flow visualization will be about, and that will be the topic for the next stream. So, any questions today? Okay. No immediate questions. Can we color zebras with this? Yes, you can. They don't really look like zebras, like the zebras you would see in reality. But yes, as a matter of fact, we use that. And I call this here the zebra method, or let the method converge toward a zebra. So we've also figured that out, that it's pretty zebra-ish. Yeah, and there's actually an interesting debate among scientists. Like if you let the result converge to the point where it's so high frequency, does that actually help, or does it just gives you brain aches or headaches if you look at this for a while? Where can I find the basics? I'm trying to find similar with shaders. It looks interesting. This one here or the previous one. So for this one here, you can find the basics in my next stream, I guess, because that's when I'll explain that. And we'll also do this in the exercise, but you can also look at the late night coding repository where we've also covered that already. I don't think we did it in a shader though. I can't really remember. I think we did it on the CPU, but the shader implementation is actually even simpler. Yeah, I mean, it gets undersampled through Twitch. I'm pretty sure that the encoding has its troubles with that. So it probably looks much better here than it does on your screen. Okay, so and I guess we're done. We're done for today. Again, if you want to know more details, next stream, which is going to be next week, next Monday, I'll continue to talk about dense flow visualization. For those who were in later and happen to be students, University of Duisburg-Essen, please fill out that evaluation form. I gave the others some time to do this, but I know that there's usually very little return, and I'd like to see more of your opinions on that stream, because that's the easiest way that I can improve the lectures, if I know what are things that you like to see improved. Okay, so then that's it for today, at least for scientific visualization. And we'll continue tonight with late night coding and hopefully finish that level of detail stuff. And yeah, that's it for this week's scientific visualization. More to come. Until then, if you haven't done so and you can, get vaccinated, stay healthy. That helps, staying healthy. See you and bye-bye.